Welcome back. Let's finish our discussion on the second derivative and concavity. Let's start out with this example here. So f of x is 3x to the 4 minus 18x squared, and we would like to find intervals on which the graph of f is concave upward and the intervals where it is concave downward, and also we want to find the inflection points. So here the domain is the set of all real numbers because f is a polynomial, and the first derivative would be by using the power rule. It will be 12x cubed minus 36x, and the second derivative would be 36x squared minus 36. So now we want to find the partition numbers for f double prime, which are the points, which are the values of x where f double prime is 0 or doesn't exist. So if we can factor out the 36 here, and we get 36 times x squared minus 1, and x squared minus 1 can be factored out into x plus 1 and x minus 1. So we see that f double prime is 0 whenever x is 1 or minus 1, and it is defined everywhere. So these are the partition numbers, and we divide the domain of f at -1 and 1, and that gives us 3 intervals here. The interval up to -1, between -1 and 1, and after 1. So here is the second derivative, and here is the number line where we have plotted the points where the second derivative is 0. Now on the left side of -1, we can pick -2, and the second derivative evaluated at -2 is, so if I plug in -2 for x, that's going to be 4 times 36 minus 36. That's definitely bigger than 0. So the second derivative is positive on the left side of -1. Between -1 and 1, f double prime of 0 is, so if I pick 0 in between, then when x is 0 we get negative, so f double prime would be negative in between -1 and 1, and f double prime evaluated at 2, that's still going to be the same as 108, so that's positive. So we obtain this sign graph for f double prime. So clearly now f is concave up from -infinity to -1, and on from 1 to infinity. So we express that by writing it is concave up here, union here. And f is concave down on the interval from -1 to 1. Notice that the concavity changes at -1 and 1. When x is -1, f of x would be 0, and when x is 1, f of x is also 0. So we see that the inflection points would be at -1, comma f of -1, which is the same as -1. Sorry. When I was plugging in f of -1, I was plugging in -1 in f double prime. So we have to go back to to calculate the inflection point. So we found that at -1 and 1 the concavity changes. So we need to find the y coordinates corresponding to these two values of x. So when x is -1, we plug that in here. So -1 will give us 3 here, -1 here will give us 18. So we get 3 minus 18, that's negative 15. And when we plug in 1, we also get negative 15. So the inflection points, one of them would be at negative 1 comma negative 15. The other one would be at 1, f of 1, where f of 1 is negative 15 as well. So these are the inflection points. And here is the graph of this function. So recall that up to negative 1, the function is concave up. Between negative 1 and 1, the function is concave down. And from 1 to infinity, it is concave up again. And these two are the inflection points. So let me lay out some graphing strategies here. So first of all, we need to analyze the function f. So that is, we need to find the domain. We need to find the x-intercepts and y-intercepts of the function. We need to find any asymptotes. We need to find the asymptotes if there are any. And we need to know where the function is positive and negative. We need to analyze the f prime, so we need to know where f prime is positive and negative. So we need to find the partition points for f prime, so those are the critical points of f, and then determine the intervals on which f is increasing and decreasing, and then find the local extrema of f by using that. And then number 3, we need to look at f double prime. Obviously, what that does is that allows us to determine the concavity. So we need to find the partition numbers for f double prime, and then determine the intervals on which f is concave up or concave down. And then we can also find the inflection points. And finally, we can use the information obtained in 1, 2, and 3 to sketch the graph of the function. All right, so let's do this. So here's the function f of x, and we want to sketch the graph of f. So first of all, the domain here is the set of all real numbers, because this is the cubic root of x. And because we are taking an odd root here, x could be negative. So that's the domain of the function f. And we can rewrite the function by factoring out x to the 2/3. If we factor out x to the 2/3, then we have to multiply each term by x to the negative 2/3. So if I multiply the first term here by x to the negative 2/3, then we will end up with 3. And if we multiply x with x to the negative 2/3, then we end up with x to the 1/3. Okay, so now notice that f of x would be 0 if either x is 0 or x to the 1/3 is x to the 1/3 is 3. So in other words, either x is 0 or so the function f is 0 when either x to the 2/3 is 0, which would simply mean that x is 0, or when x to the 1/3 is 3, that would mean that x is 9. Sorry, x is 27. So f is 0 at f has x intercepts at 0, 0, and at the point 27, 0. So these are the x intercepts. Now, so these are the points. These are the only points where f is 0. Let's figure out the sign of f. On the left of 0, what's the sign of f? Well, on the left of 0, we can pick negative 1. And if you look at f of negative 1, f of negative 1 would be, I will get, because we are squaring here, so that's going to be positive. And when x is negative 1 here, This is going to give us a negative number, so we get positive at the end. If I pick 1 in between 0 and 27, then f of 1 would be positive here, so positive. And at 27, on the right side of 27, let's say we can pick 64, and if I plug in 64 here, then I get 64 cube root of 64, and that will be 4, and then 4 squared would be 16, and here cube root of 64 would be 4, and 3 minus 4 would be negative 1, so we get negative 1 here, and 16 out of here, so we get negative 16. So basically f is positive on the left side of 0, in between 0 and 27, and after 27. Okay, so now we know where f is positive and negative. So f is positive on the interval from negative infinity to 0, union 0 to 27, and it is negative from 27 to infinity. Now here, I really don't need to use the union symbol. I could have said f is positive from negative infinity all the way up to 27, because f is defined at 0. So there is no reason to write it in this way. We could go from negative, we could write this as negative infinity to 27. Okay, so now this is f of x, and now we look at f prime. The derivative would be derivative of x to the 2/3, so that's going to be 3 times 2/3 x to the 2/3 minus 1, which would be negative 1/3 here. So we end up with 2x to the negative 1/3 minus 1. And we can rewrite this as this. So basically, if you multiply and divide this by x to the 1/3, right? So if I multiply this thing by x to the 1/3, then I'm going to get 2 minus x to the 1/3, and then I have to divide by x to the 1/3 as well. So we can rewrite this in this way. We see that f prime is 0 when x to the 1/3 is 2, and x to the 1/3 is 2 means that x would be 8, and we see that f prime would be undefined when x is 0, right here. So f has critical points at 0 and 8. Okay, we're getting 8 out of this equation and 0 out of this equation. So these are the critical numbers. These are the partition numbers for f prime. Now we figure out where f prime is positive and negative. So notice that f prime of negative 1, so we replace x by negative 1 here and here. And if we do that, we'll see that we get something negative. So it's f prime is negative on the left of 0. Between 0 and 8, let's pick 1. If I plug in 1 here, 1 here, we see that we get positive, so f prime is positive here. And then after 8, we can pick something like 27. The reason I'm picking 27 is that that'll be easier for us to take the cube root of that. So cube root of 27 would be 3. 2 minus 3 is negative. And in the denominator, when I plug in 27, I get positive, so it's going to be negative here. So we got that f prime is negative up to 0, between 0 and 8 it's positive, and after 8 it is negative again. So f is decreasing from negative infinity to 0 and on the interval from 8 to infinity, and f is increasing on the interval from 0 to 8. So clearly, because f is decreasing on the left of 0, increasing on the right of 0, notice that we have a local minimum at the point 0. And then at the point 8, on the left of 8, the function is increasing. On the right of 8, the function is decreasing. So if it is increasing and then decreasing, then we have a local max at 8. So the f has a local minimum at 0, and the minimum value would be f of 0, and f of 0 is 0. F has a local max at 8, and f of 8 would be 12 minus 8, which is 4. So this would be f of 8. Okay, so f of x is this again, and we found the first derivative. And now in order to determine the concavity, we have to look at the second derivative, and the second derivative would be 2 times negative 1/3 times x to the negative 1/3 minus 1, and negative 1/3 minus 1 would be negative 4/3, so we get negative 2/3 times x to the negative 4/3, which we rewrite as negative 2 over 3 times x to the 4/3. So notice that here we are taking the cube root of x, and then we are taking the 4th power of that. So this is an even power of x to the 1/3. So f double prime is undefined when x is 0 clearly, and it is never 0. So this is the only partition number, and so f double prime is undefined at 0, and it's never 0 because the numerator is 2. So this quantity, no matter what x is, can never be 0. So on the left side of 0, when x is negative, notice that the denominator is positive because of the 4th power here. So when x is negative, the denominator here is positive. So because of the negative here, on the left of 0, f double prime would be negative. On the right of 0, f double prime would be negative as well. So f double prime of negative 1 is negative, and f double prime of 1, for example, is also negative. So f double prime is negative up to 0 and also after 0. So we can say that f is concave down from negative infinity to 0, and it is also concave down from 0 to infinity. So f never changes concavity, so it has no inflection points. Okay, so now we want to plot the intercepts, the local extrema, inflection points if there are any, but we don't have any in this problem, and then we sketch the curve. So first of all, recall that we had the x-intercepts are at 0, 0, and 27, 0. These are the x-intercepts that we obtained. And also recall that recall this point here where okay, so let me go back a bit. So recall that we have a local minimum at 0 and local max at 8, right? And f of 8 is 4. So local max is at the point 8,4, and local mean is at the point 0, 0. So we're 0, 0 is also an x-intercept. So we are plotting those. Okay. Now what do we know about the function? We have determined that the function was so the function is concave down throughout. We know that. And in terms of increasing and decreasing, we know that it's decreasing up to 0, and then it increases up to 8, and then after 8 it decreases, right? So we can use that and say, okay, up to this point the function is decreasing, right? The function is decreasing. After this point the function is increasing up to 8, and then after 8 it is decreasing again. So it's going to go through here and come down, right? Now we know that the function is decreasing up to 0, but it is decreasing from where? As x goes to negative infinity, what is happening to the function? This is the function here, And if you look at this function, the highest power of x is right here, 1. So if I, so when x goes to infinity, when x goes to negative infinity, then this is the dominant term. So when x is negative big, f of x will also be, when x is negative big, because f of x would be positive big. So that means when x goes to negative infinity, f of x goes to positive infinity. So on the other hand, when x goes to infinity, again, this is the dominant term, so I'm going to ignore this guy. When x goes to positive infinity, f of x goes to negative infinity. So we know that it is going to go down forever here, and it's going to go upward forever as x goes to negative infinity. So we know that the graph should be like this. So it is concave down. So it's going to be like this, and then up to 8 it is increasing and concave down still, and then it is concave down all the way, and then it is after 8 it starts to decrease. Okay. Okay, so remember that the point 8 right here is one of the critical points of f. So that's where the derivative was 0. So that's where the slope of the tangent line would be 0, which makes sense from the graph. Okay, so that's the graph of that function. All right, so this is it on concavity. Oh, so I did label them that I forgot. Okay, so f decreases, concave down, f increases up to this point, concave down, decreases afterwards again, concave down, and so on. So local minimum at this point, local max at this point. This function does not have a global max or min on its domain. Okay, so that's the end of it, so I will stop here and hope to see you in the next video.